let's see here, a color change or a change in your temperature. Let me go back up here to the last two and put formation of. So formation of light, formation of a gas, solid forming, color changes, change in a temperature. And that we actually did our very first unit. So you've seen those before. Okay. Chemical equation, chemical reaction. A reaction is just simply where you put two things together and you get something new out on the end. The chemical equation is still the reaction. So I'm going to do RXN, that's the abbreviation. The reaction in formulas and symbols. Reaction in formulas and symbols. So instead of writing out the entire word, we're going to use the symbols and the formula equations to make things a little bit more simpler and easier to work with. Okay. Parts of the reactant, reactions, the reactant, the first part is in the beginning. So what takes place, what you start with. The product is what is formed. What is formed at the end? What do you get out of it? Okay. A catalyst is something that speeds up a reaction time, but it's only in some. Catalysts are not very common, but they are out there. So what I've got here is I've got an example here. So the octane and the oxygen, those are your reactants. And the backside, the water and the carbon dioxide, those are your products. Okay. Now, in order to figure out whether or not a catalyst is present, you are going to have something above the arrow, okay? So for example, for this example that I have, if I look at my arrow, there is nothing there above it, so this one has no catalyst. It's as simple as that. Is there something above it or not? Exothermic reactions. These two are all about energy, so whether or not something gets hot or cold. Exothermic reaction is when energy is released. Gets hot. Endothermic on the other side is when energy is absorbed. Gets cold. Okay, so instant ice packs, when you pop the disc and shake it and it gets cold, it's an endothermic reaction. Your hand warmers here in the wintertime, you shake them or whatever the manufacturer says to do, it gets hot, it's an exothermic reaction. Okay. If energy is placed with the reactants, it's an endothermic, and if it is on the right with the products, it is an exothermic. So what I mean by that, let's just say we have A plus B goes to C plus D plus energy. Okay, the energy term is on the right side with the products. This is an exothermic reaction. Exothermic. Because it's simply with the product. So that's what I mean by that the energy term is placed on either side. Activation energy, okay, is the energy needed to start a reaction. So if you have to stir it or if you have to heat it, that energy that you are putting in it to get to the reaction to go is actually your activation energy, okay? And so what we have here, we have this lovely little diagram, this little graph here. Here's what we've got. I'm going to show activation energy. We're going to start out at some energy level, whatever that is. The reaction is starting, and then we have to get it to go, so we get this big hump, and then the reaction proceeds and it finally ends, okay? If we extend this line where we started out at, this hump, that entire hump, is the activation energy. Activation. And we abbreviate it E sub A. But that hump is your activation energy. A catalyst, again, a catalyst is something that speeds it up, so accelerates the reaction, decreases activation energy. So what I mean here, okay, I'm just going to draw what I just drew up above. There's our activation energy. What happens with a catalyst, okay, again, we start at the same level, but now our hump is a lot smaller. So we start and end at the same place, but the hump just gets smaller. Determining exothermic and endothermic, you can tell just by looking at a graph what it is based on, do things end higher or lower than where they began, okay? So exothermic, actually the two graphs that I've already done, those are an exothermic, okay? Start at some level, activation energy, end at the bottom. See, lower than initial. Exothermics end at a lower energy level. Continuing here, if you extend that very first line, that hump, we already talked about that. That's your activation energy, okay? But if you extend the bottom line where you stopped, okay, and since it's exothermic, this is your energy released. So how hot did it get? Okay. Endothermics end up higher than where we started. So again, start at some level, have our hump, but now we're going to end at a higher place. Again, if you extend out the first one, the hump here, that is your activation energy, your E sub A. And then this time, this is your energy absorbed. How much energy is brought back in to get cold. Physical states, this should be pretty self-explanatory. Are things solid, liquids, or gases? You've got your symbols here, and that's what you'll be practicing on your worksheet, is doing these symbols. So solid, liquid, and a gas. Aqueous is anything that's dissolved in water, okay? Aqueous is used all the time. The only thing that we're going to work here with a liquid that's going to get the L is water, okay? Everything else, all the other liquids are aqueous. They're dissolved in something. So don't get happy with the L's, okay? Because only water gets the L. Everything else gets an aqueous, that it's in a liquid state, okay? So on this example, you can just see here the phase labels that I put on there. They're always after the symbol, and they're always in parentheses, and they're always in cursive, okay? Or italics, however you want to say that. But afterwards and in parentheses, okay? All right, so this is kind of what you're going to be doing today. We're not going to go into doing word equations, so you can just go ahead and cross that part off, because we're going to hop right into the formula equations. And when we do formulas, that means we've got to write the formulas out of all that nomenclature stuff, all that naming and writing formulas that we did, that you thought you could maybe shelve it for a while, has got to come back, okay? Again, that Roman numeral there of the lead to chloride. Give me a second, my computer is being weird. All right. So let's write our formulas. Lead to chloride. So again, the lead is a +2, chlorine is a -1. So my formula equation for the lead to chloride is PbCl2. Okay. Sodium phosphate +1, and phosphate is PO4 with a 3-, which is going to make this Na3PO4. Reacts to produce lead 2 phosphate, which is going to be Pb3PO4 2, and sodium chloride, NaCl. And there is your formula equations. Now, the last thing here before I actually show you your worksheet and give you an example of it, these 7 diatomic molecules. These molecules, when they're found in nature, they're not just found with the element. They are always bonded to themselves. So you get 2 of them. So here are the 7, okay? We've got hydrogen, so H2, okay? These always have a 2, hence the diatomic, okay? Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, okay? All of those, when they're by themselves, and it's only when they're by themselves, okay? It's that element symbol and a 2. Okay, so when you see the word oxygen, it's not O, it's O2 because it's one of these special ones. And I'll show you that on your worksheet. So what I'd like you to do now is I'd like you to hit pause for a second. I want you to go up to the front of the room, and I want you to grab your formulas with phases worksheet, and I'm going to go through question number 1 with you so you know exactly what you need to do. So press pause and go get that while I set up for the next part. Okay, so before we get to this, okay, I want to write down these diatomics again for you, okay? Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, okay? And then the other thing that when I want to mention, these 7, these are in the gas phase. So as we're putting phase labels with this worksheet, when you run into one of these 7, they are gas. Okay, and so here we go. Let's write the equation. Don't worry, we're not doing balancing. Okay, so you're just writing the equation. We haven't gotten into balancing yet. Okay, so here we go. Aqueous sodium bromide. So sodium bromide, +1 for sodium, bromine is a -1. Always check your periodic table. NaBr, and it said it's aqueous, so our phase label is AQ. Reacts with chlorine. Now, here it is, okay? Chlorine is just by itself. So when it's just by itself, in this case, it is Cl2 with the gas label on it, okay? Again, it's only when it's just chlorine. It's not with anything else, okay? Reacts to produce. That to produce is the clue for the arrow. And then it produces aqueous sodium chloride, which would be NaCl, and it says it's aqueous. So it's a label of AQ. So what you are doing with this worksheet, okay, is you are simply writing the formulas, okay, and then putting the phase labels that coincide. And again, this the phase labels should be given to you. It should be pretty easy for that. The only thing that you might want to make a note of is, like in this one,